Where we left off last time was here. And this was a center of mass problem. And it's one where symmetry is our friend. And we determined early on the center of mass would be somewhere on this z-axis. And so that saved us 2 of the 4 triple integrals that we would otherwise have to compute, right? The density here was proportional to the distance from the the xy plane. And the distance from the xy plane is just the z coordinate, all right? And so to do the mass, you put the density in here, right? And then all this stuff, this and that just comes along with every spherical coordinate problem, right? And we had worked this through where we got k over 4. We were in the middle of this last time. And here we are integrating our rho. Our rho is kz. And there's another z here. Okay. Well, we got to get rid of z's. And z is rho cosine phi. So this z squared, z times z is this z squared. And the k we put outside. And we were going to integrate this with respect to rho. All right. And so where we pick up is 4k integral 0 to pi over 2. Let's get the trigonometry stuff out of here. Cosine squared phi sine phi. Then we have a rho squared from these parentheses, another rho squared. That's a rho to the 4th. Integrating that is rho to the 5th divided by 5 from 0 pi over 2. Wait a minute. No. We have a typo. We have a definite typo there. That would be unfortunate. The typo is we left off a 0 to 1 here. Sorry about that. Yeah. And so we have another integral in here, 0 to pi over 2. Okay. That did not look right. My mistake. But nonetheless, we bring this trigonometric functions, those out here. And we're left with a rho here that gets squared, and then a rho squared. That gives me rho to the 4th. Integration to rho to the 5th over 5 from 0 to 1. And then here we're going to have d phi, d theta. And this is just 1, right? All right. And that gives us 4k over 5, integral 0 to pi over 2, integral 0 to pi over 2, cosine squared. You know what I'm going to ask? Phi sine phi d theta. How do you integrate that? How do we integrate that? It's not particularly difficult. Because we have a cosine to a power times sine, which is almost its derivative, right? So we need to put in a negative sign right there and a negative out here. And then we're going to have cosine. This gives us cosine phi squared times minus sine phi. That's cosine to a power times its derivative. Derivative of the inside. So that gives us minus 4k over 5. I'm going to get a cosine cubed over 3. So I put a third out here. Integral 0 to pi over 2. Cosine phi cubed 0 pi over 2 d theta. And we've seen this before. When you plug in pi over 2 into cosine cubed, you get a cosine of pi over 2, which is 0. Cubed, 0. Minus, which you get when you plug in the 0, which is going to be a 1. So that integrates to 1. That happens a lot in these. Now, of course, we're not doing extremely complicated spherical coordinate problems. These are not extremely complicated. They're enough for us to make mistakes on. All right. And so that gives us, oh, I'm sorry, we have a typo here. Getting cocky. That's a minus 1. Yeah. So that gives us 4k over 15 integral 0 to pi over 2 d theta, which is 4k over 15 times pi over 2. And that is a 2 pi over 15. And so that's our mxy. So we're going to use that here in a second. We know that x bar and y bar are 0. Z bar is mxy divided by m, the mass. That is 2 pi over 15 divided by what we got up here, k over 4. Oh, we dropped a k here. That means we dropped a k there. And that's k over 4. And that is going to be 2 pi, the k's go, over 15 times 4 over 1. Right? And that is 8 pi over 15. Ergo, the center of mass is 0, 0, 8 pi 15. Interesting that the k's cancel. So you get the same center of mass no matter what your constant of proportionality is. And except for the homework on the next slide. Some love for you for next time. All right. That's all we're doing of chapter 14. We got this right here. We'll get rid of this, delete that slide. Right, we're not doing the 14.8 Jacobians. It's interesting. It's usually left to our differential equations class. We're not going to do that. So basically what we covered was the spherical coordinates, and you're going to be responsible for spherical and cylindrical coordinate type integrals, because I want to make sure you know how to distinguish when one is appropriate versus the other. Get rid of that. I should have left that open actually, but oh well. Chapter 15. 15 gets very interesting. We're only going to have time to scratch the surface of chapter 15. But at least we'll scratch. All right. Vector analysis. This combines lots of stuff from all the calculus you've had. But it involves a lot of a lot of Calc 3. Vectors, obviously. You're going to have normal vectors and so forth involved in here. You're going to have all kinds of cross products and dot products, that kind of thing. You're going to have double and triple integrals. All the different chapter 8 methods of integration pop up in here. All right, so the principal thing we're going to be working with in chapter 15, I gave you these slides before we left, I believe, right? So the main thing we're going to work with here that's going to be new is a vector field. Vector field, right? And a vector field assigns a vector to every point in the field. Meaning, if you have the Cartesian flat coordinate plane xy, to every point xy will be assigned a vector. All right. If it's xyz, space, like right here, to every point xyz will be assigned this vector. Okay. Notice we designate vector fields with a capital bold F. Now you don't have to do the bold, but the capital F as opposed to a little f to distinguish it from an ordinary multivariable function. All right, so it's going to assign every point in a space a vector. There's 3 interesting examples that the book gives. Velocity fields. Excuse me, I'll blow my nose. Velocity fields. It's something we haven't studied, but particles rotating about some center of mass. Certainly this applies to planetary motion. There's lots of things that orbit our planet. Okay, lots of small stuff, right? Not just satellites, by the way. At any point, you see at any point around the center of mass, at any point you pick, there is a vector associated with it. And it looks like the further you go out, the longer the vector. Gravitational fields are very interesting. We're going to be working a good bit with these. I'm going to leave most of it for Dr. Kite's physics class, okay? But gravitational fields are interesting because the strength of the field depends on the masses of the 2 objects that are attracting each other. Right? Newton figured out that any 2 masses attract, right? So any 2 bodies are pulling toward each other, right? So you have a table that's sitting on the floor, on the earth, so to speak, The Earth is pulling the table down, but the table is pulling on the Earth up. Now, their relative pulls, so to speak, are inversely, I guess directly proportional to their mass. So the Earth is what? Trillions and trillions of times, has trillions and trillions of times the mass of a table, right? So its pull of the table down is much stronger than the table's pull of the Earth up. If you were to drop a baseball from, say, 5 feet, right? The baseball goes down, of course, by gravity, but not by much. But the Earth actually comes up, right? It's pulling the Earth up. It's exerting a force on the Earth. And I doubt if you dropped a baseball from 5 feet, whether the Earth would come up more than a molecule or something. It will be an extremely small amount. Don't wait for a jerk under your feet. However, there are masses that do pull the Earth around, right? The sun, for one thing, much more massive than the Earth. It determines a lot of the Earth's path, but also our moon. Our moon. It's 1/6, I believe, the mass of the Earth. But that's still pretty big by earthly standards, right? Space is absolutely amazing. There are stars out there and celestial bodies that the single celestial body is bigger than our entire solar system. All right, so that's kind of the scales that are out there in the universe are just nuts. So anyway, this force field is given by this, right? Right, and it's got a vector u, right? U. That's interesting, right there, right? All right, let's just go down some more. There's one more. What? Wait a minute here. I believe there was one more there. Okay, what there was. Vector field, aerodynamics, fluid dynamics, the air passing over a vehicle, right, has a vector associated by the disturbance that associated at any point near the car because of the disturbance that the car creates going through the air. Same with fluid, right? Let's have a look at this. Graph the following vector field. Now, when we say graph something like this, we mean draw enough of it so that an observer understands what's going on. Just a second. Yeah, this classroom is about 10 million degrees. I just turned on the AC. I hope that doesn't come through too loudly on the microphone. Right, so let's have a look here. There's our xy. And this vector field, at any point, the vector is going to be minus the y coordinate in the I direction, plus the x coordinate in the j direction. What is that? All right. Now, the comment here, I hope, is useful. You could plot vectors at just random places in the plane, and you might see a pattern that way. You probably would eventually. However, I like it better to plot vectors of equal magnitude, or I like doing vectors along vertical and horizontal lines. For example, 1, 2, 3, 4, minus 1, minus 2, minus 3, minus 4, 1, 2, 3, 4, minus 1, minus 2, minus 3, minus 4. Right? Let's take a look at the point, say 1, 1. At this point right here, 1, 1. The vector is going to have the x-coordinate is 1, the y-coordinate is 1. So the vector that's going to be there is going to be minus 1 in the I direction. Now the I direction is the x direction. So it's going to be minus 1 that way and positive 1 in the x direction. So it's going to be that way and then this way, right? So that gives the net vector to be like that, right? All right. Now let's move over. Let's move over 1 to here. How's that vector going to change? The y is the same. The y is the same. So it's going to be negative 1 in the x direction, which is that way, and positive 2 in the y direction, that way. So that the sum of those two vectors is like this. So those bold vectors are our vector space. Those bold vectors are our vector space. Well, how about if I did this vector here on the y-axis? The y-coordinate is still 1, and so it's going to go over 1. The x-coordinate is 0, so it doesn't go up and down at all. So it goes like that. All right? Yeah. All right? If I go over 1 more, if I go over to here, minus 1, 1, my vector is going to go over 1 because y is the same. The x-coordinate is now negative 1. It's going to go down. So the vector field, the vector in the vector field at that point is like that. All right, that's interesting. How about if I go along the x-axis? How about if I start, say, at the origin? I'm going to do a different color. At the origin, 0, 0, I have 0. Kind of boring. All right. At 1, 0, my I is minus the y-coordinate, but that's 0. Y equals 0 along the x-axis. My x is 1, so it's going to go straight up 1. Up 1. How about if I go over here to 2? It's going to go straight up 2. Over here to 3, it's going to go straight up 3. At minus 1, goes down 1. Minus 2, goes down 2. Sort of a strange looking vector field, right? Let's go down to y equals -1. So along this line here, let's start right here. Okay. Let's start at -1, 0. What's the vector going to be there? The y coordinate is -1. So the I is going to be minus a -1, 1 in the I direction, x is 0. So that's going to go 1 that way. Okay. How about right here at this point, -1 or 1 -1? Y is -1. So it's going to go 1 in the x direction. And then the x coordinate there is 1. It's going to go 1 in the up direction. So it's going to go up like that. So that vector looks like that at that point. Okay. All right. Let's go over here to this point. -1, -1. This can be slow and tedious. -1, -1. Y is -1, so it's going to be minus a -1 in the x direction. That's a 1 that way. And then x at that point is a -1. That's going to go down. So the net vector is going to be like this. All right? You can pretty much see that the next one here is going to be 1 over and down 2. Like that. It's going to be a mirror of those green ones. Okay? All right? How about if I go to -2, 0? How about if I go to this point right here? X is 0, so y is -2. So that's going to be 2 in the x direction, like that. See how this is working? Right? If you went up here to 2, it'll probably be like that. Right? So you're starting to see a spiral pattern emerge. This is going to be over 3. Right? If I did, let's say, this point right here, -2, 1, it's going to be +2 in the x direction and 1 in the y direction. So that's going to be like that. Okay. All right. So it's going to be a spiraling sort of pattern, right? This one here is going to go 3 units over. This one would go 3 units down. And you get the idea. Okay. So it turns into a spiral. That is not evident when you just first look at it. All right. Any questions on that? It's a little bit tedious. Compute. What is this again? What is that?
The gradient?
Yes, we have a winner. Either that or somebody who had mercy on her teacher and decided to answer our question. Appreciate that. That's the gradient. What's the gradient again? That's the gradient of a function is a vector, you remember? Okay. Remember the gradient of f of x, y, z is fx, it's a vector, fy, fz. Right? And so in this case, yeah, in this case it's going to be fx is the derivative with respect to x of this buzzard up here on the top right. Yeah, here. So this is going to be, you're going to see a pattern, I think. But I'd be careful here. This is minus gm, and then we have x squared plus y squared plus z squared to the minus 1/2, right? So the g and m are constants. And so the derivative of that with respect to x, the partial with respect to x, we're going to subtract 1 from the exponent and get minus 3/2. And the derivative of the inside, the derivative of that, with respect to x is 2x. It will pop out. And so that's going to be what? Okay, the derivative here, you're going to take the minus 1/2 down. Here, I'll do one the long way. Minus gm. Bring the minus 1/2 down. X squared plus y squared plus z squared to the minus 3/2. And then the derivative of the inside with respect to x pops out, a 2x. Those cancel. All right? Now, just for a second, leave these next to blank, because you're going to see a pattern. Right? These negatives cancel. The 2's cancel. You got gm on top times x divided by x squared plus y squared plus z squared to the 3/2. Come. Now, what's going to be different when you take the y partial? You're going to get a y right here, and everything else is going to be the same. You're going to get a 2y come out instead of a 2x. And so I think you could see that the y partial is going to be gmy over the same thing. Come. GMZ okay. All right. So look for those patterns. That is the gradient itself forms a vector field. So the gradient of a real valued function is a vector field. So that's a vector field that with which you're already familiar. Okay? Oh, here's the third one. I knew there was a third one. Electrical force fields. Coulomb's law. All right. This is pretty interesting. That it you have two particles, Q1 and Q2, with charges Q1 and Q2. The forces between them are that. All right. And now R is a very simple vector valued function. Okay. And this U is just the magnitude, I guess, and direction of the, it's a unit vector in the direction of R. Right? Note that an electric field, force field, is the same form as a gravitational force field. That's the same form as this. Right? It's the same form. You have a constant at the top. The bottom is a it's the magnitude of a vector valued function. Now, if you go back up here, this is the magnitude squared of what? That's the magnitude squared of what? Well, they don't tell you what R is here. Well, R would have to be xi plus yj plus zk. Right? And this thing down here is the magnitude squared. Right? Very similar, see, to that. Now, inverse square field, it turns out that, well, you just saw two of them. Gravity is an inverse squared field, which we just said. But what does that mean? That means when you go twice as far away from a body that has a mass, its gravitational pull is 1/4 of what it was when you started. 1/4. If you go 3 times as far away, it is 1/9. Now you might say, wait a minute. If I've got a baseball 2 feet off the ground, it's got a certain gravitational pull. The earth is pulling on it. Of course, it's pulling on the earth a little bit too, like I said. If I go from 2 feet to 4 feet, are you saying the gravitational pull is 1/4 when it's twice as far off the ground? No. Because this works from the center of mass. So, for example, if we just take a minute and assume that the earth is a sphere, which is not quite, a baseball 5 feet off the ground, let's see, the earth is around 24,000 miles around. That means its radius is roughly 4,000 miles. All right, so 5 feet off the ground, it has a certain gravitational pull from the earth. you would have to take it another 4,000 miles in the air for it to be twice as far away from the Earth's center of mass. So if you went 4,000 miles off the surface of the Earth, then the Earth would have 1/4 of the pull on the baseball as it did on the surface of the Earth. Right? So you got to go by centers of mass, not solely by its distance from the surface of something. So lots of things work with inverse squares. Lots of things do. Sound does, by the way, right? Sound does. As you get twice as far from something, the sound is 1/4. Now, sound is measured in decibels, which is a logarithmic scale, and that gets a little wonky to work with. It's easy once you do it, but we don't teach it, so most people don't know how. All right, definition of an inverse square field, what you just saw. An inverse square field, if you double the distance, the force is 1/4. If you triple the distance, force is 1/3. Right? Inverse square field. A lot of them occur in nature. The definition of a conservative vector field. All right. No, it's not a vector field that is pro-life and voted for Trump. That's not the kind of conservative we're talking about. A conservative vector field has some great properties. So a conservative vector field, capital F, is a vector field that is the gradient of some real valued function, little f. Okay? So back up here, look at this gradient, right? This is the gradient of f. And so if we call this vector field capital F is conservative. And what that means, it's conservative because it's the gradient of this function here. Right? So a vector field, F, capital F, is conservative if it is the gradient of some differentiable real valued function. Now, the function of which it is the gradient is called the potential function. So here, f, little f, is the potential function of big F. Right? Big F is the gradient of little f. Little f is the potential function of big F. Capiche? Right? To channel my Neapolitan mother-in-law, late Neapolitan mother-in-law. Okay, compute the potential function for this thing you see. What's the potential function? Well, wait a minute. The potential function, little f, is the function of which big F is the gradient. What? The potential function little f, is the function of which big F is the gradient. Well, let's see here. If that's the gradient of something, it may pay to rewrite this. This could be rewritten how? Right? And all right. What does that mean? Well, let's see. This is little fx. That's the x partial of my f. That's the y partial of my f that I'm looking for. This is the z partial of my f. All right. Hang with me a second. If I take the partial with respect to x and get this, what did my f have to be? Let's say that a different way. What's the antiderivative of this with respect to x? What is the antiderivative of that with respect to x? Remember, with respect to x, y and z are constant, as are g and m. Right? Well, I'll give you a hint. With respect to x, the top, if I put a 2 there and a 1/2 here, the 2x is the derivative of the bottom. So little f, x, y, z would have to be something like a logarithm, right? It would have to be a 1/2 gm natural log of x squared plus y squared plus z squared. Let's try that out. I claim this is the antiderivative with respect to x of that. Well, if I were taking the derivative of this would go in the bottom. So I'd have x squared plus y squared, I'm writing in yellow, z squared. And I would have the derivative of that on top with respect to x is 2x. And then I got the gm and 1/2 on the outside. Well, that looks an awful lot like that. Right? Or actually this. Another way to try this on is take the y partial of this. What are you going to get? You're going to get GM on top, this in the bottom, right there, and the derivative with respect to y is 2y. That's going to be in the top. And then I have a 1/2 out there to make it a 1y in the top. So this is my potential function. That is my potential function. And so capital F, note, last thing, note, capital F is conservative. Since capital F equals the gradient of little f. So this vector field here is conservative because we just showed it was the gradient of a differentiable function, little f. All right, we're out of time. I will see you Friday. Nothing tomorrow. You stay safe. Don't forget to wash your hands. Do everything your mama says. No. All right. Take care, guys.
Thank you, Mr. Miller.
Thank you.
All right.